So here's the pre-exposure for 8.3. I want to do a quick review of infinite series. Remember that every series has a sequence of partial sums. And it's an evaluation of that partial sum sequence. Right, there we go, Sn. If the partial sum sequence converges to a limit, so if the partial sums sequence converges to a limit, then the infinite series does as well. So if that converges to L, then the infinite series does. If the partial sum diverges, then the infinite series diverges. Alright, so your procedure is to evaluate the infinite series. You find the formula for the sequence of the partial sums, and then you evaluate the limit of the partial sum. So what we're going to look at pretty much in 8.3 is the geometric sum, which we already looked at the geometric sequence. But the geometric sum, we're going to look at a finite number of terms to see if we can derive a formula that represents the partial sums. So in looking for a finite sum, I'm going to redefine Sn and show you this algebra, how we derived it. Okay, so this should be familiar to everybody. This is your geometric pattern. And I'm going to rewrite the sum in notation, shorthand notation, which is k equals 0. Now the upper limit is n minus 1. And here's your geometric term. So the goal is to find a formula for the geometric sum and then extend it to the geometric series. Alright, so that's our goal. Write that down. So the goal is to find an explicit formula. And then we'll extend it to the geometric series. So we'll go from the geometric sum to the geometric series. So then we'll extend it to the geometric series. Okay, so what does that algebra look like when you're working with, and this is actually proving a formula. We'll do a little bit here. So the algebra for the formula of the geometric sums is going to look like this. So your first equation is your partial sum for the geometric, which is a plus ar plus ar squared plus ar cubed on out to ar n minus 1. So that's equation 1. If I multiply both sides of this equation by r, so I'm going to multiply both sides of the equation by r. Then the second equation, I'll call it equation 2, becomes r Sn, and then we're going to multiply everything by r, so this term increases. And the last term, adding exponents, becomes ar to the n. So now I'm going to, second step, I'm going to subtract equation 2 from equation 1. And I'm going to set it up a little bit easier so that you can see what's going to happen here. The beauty of this proof. Dare I say proof, right? We are doing some proving, and we'll do a lot more when we get into chapter 9. So here's equation 1. And I want to subtract equation 2 from equation 1. So I'm going to subtract R, Sn, and I'm going to line up the terms here, okay? So that you'll see what's going to happen. Okay? Don't forget to distribute the negative sign. Right, so you've got to distribute that negative sign into all the terms on the second equation. And when I do that, you'll see, grab another ink here, that these terms will cancel out when you perform the subtraction, right? And what you're left with is this leading term and this ending term. So the result of this is Sn minus R Sn equaling A plus A R to the n. And let's factor out like terms, and I get Sn equals 1 minus R, and I'm going to factor out an A, and I get a 1 plus R to the n. Solving for Sn, I get the formula A times 1 plus R to the n over 1 minus R. So this is the explicit formula, which you'll see is important, and what makes the geometric series so nice to work with is that we can actually find this explicit formula. There's only a couple sequences that this pops out for. Alright, so that's the explicit formula. Now we're going to take the limit. So now you're going to take the limit of this thing. Okay? I'm going to pause there for a minute. Okay, I'm back, and I just realized I found a problem in my signs. Right? I forgot to distribute the negative sign in for the last term. So let's clean that up. And again, I don't know why I make these videos so late. Alright, so this formula was wrong. It was off by the sign. It's 1 minus R to the n over 1 minus R. So now take the limit of the explicit formula for the sequence, partial sequence of the sums. The sequence of the partial sums, rather. So taking the limit of the explicit formula, all right, you notice that the only term that has an n in it is right here. And we worked with this before, so we're going to concentrate on the term with the r to the n, since that's where n is going to vary. And we look at the limit as n approaches infinity of r to the n. Okay, and you remember from when we looked at the geometric sum or the geometric sequence that you had basically 3 scenarios that broke out, and that was if the absolute value of r was less than 1, then the limit converged to 0. If r was equal to 1, then the limit was 1, and if r was less than or equal to -1 or r was greater than 1, then this did not exist. This limit did not exist. So we're going to look at 3 cases, and that gives you what happens with the geometric series. And I'll just summarize it, and then that's going to be it. So in summary, for a geometric series, it only converges. So this is the bottom line now. I'll grab another for geometric. All right, if the ratio r is less than 1, then the series is going to converge.
Mommy.
1 second, guys. What, hon? So to wrap this up, if r is less than 1, then the series, the geometric series, is going to converge, and it converges to a over 1 minus r. Okay? If I guess I don't have any space here. If the absolute value of r is greater than or equal to 1, then the series diverges. Okay, diverges. So all the work in proving that boils down to, this is what you really need to know right here. That if you have a geometric series and r is less than 1, then it's going to converge, and it converges to this value. If the absolute value of r is greater than or equal to 1, then it's going to diverge. And we'll work through examples in class.